Welcome back. So if you remember, last time we have different kind of setup, but today we will use again this platform basically. Okay, so let's see. So if you remember last time, we discussed infinite series, and also we discussed convergence tests for positive series. Okay. But today we will basically focus on, we will deal with more on series, but we will focus on the concepts of absolute and conditional convergence. Okay, so let's see. Um, so the first problem, so we have parts actually for the first problem. As you see, we have a bunch of series, and we are going to try to understand the behavior of those series. I mean, if you like, we try to understand which of the following series converge absolutely, or maybe conditionally converge conditionally, or maybe some of them diverge. Okay, so we will try to understand those behaviors. Okay, um, fine. So let's see for part A, so the solution, and part A. So part A, what we are given is the following. So we have a kind of a series, which is maybe a first observation. So n pi, divided by n ln n. So this is our series. And if you look at carefully, because of the properties of cosine, so this series can be rewritten in this form. So this is nothing but minus 1 to the n, divided by n ln n. Okay, so we have a series like this. This is another way of writing this series basically, and we just let this n term to be a n to be minus 1 to the n, and divided by n ln n. Okay, and we try to understand the possible behavior of this series. Okay, first let us check. This is the first thing you need to check actually. So oops, what is it? So we have some ln. Okay, it is gone. Okay, fine. So we need to check absolute convergence first, which means that we need to check behavior of this series first. Okay, so let's check. And if you look at carefully, so what we have here, um, what we have, maybe I should maybe observe that this thing is nothing but a series like this, right? So this is 1 over ln logarithm, logarithm n and n. Okay, fine. And remember, we can use actually, what is it? Integral test, right? So just just look at the corresponding improper integral, if you like, right? I mean, n starts from, maybe I should write it down. N starts from 2, right? Not 1. N starts from 2 here, and similar here. And therefore, this integral starts from 2. Okay, let me write it down. So where is it? Okay, 2 infinity. Let's try to understand the improper integral of this function, with this integrand, right? Remember, if you really understand the corresponding improper integral, then you can understand the behavior of the series of interest basically. And what is it? If you remember, this is how we deal with improper integrals. We just consider actually definite integrals, I mean the proper integrals, if you like this. And when we evaluate this proper integral, then look at the limit. Fine, so let's try to understand. So what is it? I need more space here. Okay, fine. So let's try to understand. So we have 1 ln x times 1 over x dx. If you do the substitution, which is just, you just let 1 over x to be u, blah, blah. Oops, it's not true, of course. You just let ln x to be u, and then you compute the rest. And then we end up with limits. I just skipped this part. This is the usual integration tricks. And what you have, this is just, okay, ln x. So this is your basically antiderivative, right? So here, so when you differentiate this thing, you end up with the other term. Okay, fine. So this is your antiderivative basically. And what does it tell us? If you compute limit r approaches to infinity, so let's compute the term inside. So this is just ln r, right? So everything is fine. So ln 2, so ln 2 is just a finite number, but we have ln r here as r getting larger and larger and larger in a positive direction. So this is just infinity. So what does it tell us? The corresponding improper integral has a kind of a divergence behavior. Therefore, the corresponding series, so by integral test, remember, by integral test, the corresponding series, which is this, okay, x, oops, n ln n, right? And this is exactly absolute value an is divergent as well, is divergent as well. Okay, so this is basically what integral um, test tells us. Okay, so what does it tell us? Actually, we conclude that so what, right? So we conclude nothing. So when you look at the so absolute value, and you look at the series with this absolute valued sequence here, and it basically it diverge, right? It diverges. So what does it tell us? Nothing. So, but you cannot conclude that the corresponding series is divergent as well. So this is wrong. So, but the series, the original one, can still be convergent, can still be convergent, but it is not absolutely convergent. So, but still, there is a possibility that this thing is convergent. Therefore, we need to use something else to understand the convergence behavior. So absolutely convergence tells us nothing because we end up with a kind of a divergence behavior. So it tells us there is no conclusion to be used. Therefore, let's look at the second possible approach. So the second thing is check conditionally convergence. Okay, so first thing we check the absolute convergence. Now we check the conditionally convergence. So, but we just observe, okay, observe that. So let's observe the following. So actually, if you look at carefully, so this series is alternating, right? So therefore you have something like this for all and on the other hand, if you look at carefully, so absolute value a n plus 1 is just, okay, 1 over n plus 1 logarithm n plus 1. But we know that the logarithm itself is a kind of an increasing function, right? Therefore, when you look at its multiplicative inverse, or if you just switch upside down, and then, okay, you have something like this. So logarithm n, but this is nothing but absolute value a n. So what does it tell us? A n is decreasing. So it says that this thing basically decreasing sequence. And the last thing, if you look at the limit n of this thing, and you can easily see that this is nothing but limit n, okay, when 1 over ln n times n, this is just 0. And so this is nice. So this is actually, so everything is fine. Actually, we can use alternating series test. right? So all conditions are satisfied for the hypothesis, actually, for the hypothesis of alternating series test. So by alternating series test, so for the exact statement, of course, you should go back and check the lecture notes, alternating series tests. We conclude that this thing, okay, AN is convergent. But remember, it is not absolutely convergent, but it is convergent. And so in this case, we say that, so that therefore, we say that AN is conditionally convergent. Okay, that's all. So if you go back, what we did, we just first check here, where is it? So we check here, here we just first look at the corresponding, so we just look at the absolute value of the n term. And this is the first thing we checked, basically. Maybe I should use, okay, what is it? Okay, fine. Okay, this is the first thing we checked. And then we basically see that this is not absolutely convergent, but by using alternating series test, or by using some other technique, if you like, we just show that the series itself is convergent, but not absolutely convergent. Okay. So what about part B? So what about part B? So for part B, remember what is given. What is given is the following. So we are given the following series, basically. So we have, again, cosine and pi, right, divided by, so what is it? N square root n, right? N starts from 1 now. And by using the same reasoning, we can really write down everything in this form, right? So because of the properties, cosine and pi is depending on n, it is either 1 or -1. And so we are done. So we have indeed rewrite everything by just, get rid of this cosine term. So, which is nice, right? So by the similar reasoning, by similar reasoning in part A. But now, so let's see what we have. So as before, let's check the absolute value, right? And let me call it, maybe I should, so as before, we just let this n term to be this -1 to the n square root n. Okay, we have this. And of course, first thing we need to check is the corresponding term with an absolute value, right? And if you check this, you see that just observe that the absolute value gives us something like this. What is this? 1 over n. Okay, let me write it down in this way. And starting from 1, but this is very well known, right? So this is very well known series. This is just is convergent, which is convergent. Why? By p-test. Okay, so this thing is convergent by p-test. So we are lucky. So when we look at it, the absolute value of the corresponding sequence, and we look at the corresponding series, of course, at the same time, and then it end up with basically the following fact. So it is convergent, and then we say that therefore the series is absolutely convergent. So so the series, the original one, is absolutely convergent, and so it is convergent by theorem. It is convergent. Fine, this is basically the advantage of absolute value. So if you have something which is absolutely convergent, then we can automatically say that, okay, the original one is convergent. Okay. Fine. So let's see the next problem. I mean, the next, if you like, there are. I mean, this is part B, right? So this is part B. Let's move to part C. So what is it? So I mean, what was it? So what we are given? So we are given a series in this form, right? So let me check. Okay, something like this, right? So you should check as well. Okay, fine. So this is our series, right? So something like this. And if you like, we just let a n to be this term, this ugly term, 2n factorial divided by, okay, 2 to the n times n factorial times n. Okay, fine. So as before, check absolute convergence, okay? Just check the series itself. Okay, n starts from 1, I guess, so rest is the same. Let's check this series, okay? Let's first check this series, but this is nothing but, okay, n starting from 1 with this absolute value. We just get rid of minus 1 to the n term here. Other terms are already positive, so I'm not going to write it down, the absolute value symbols. So basically that's it. This is our series. And if you have something like this, you can use actually, if you remember, um, you can use what is it? Ratio test, right? And now just look at the following ratio, right? Limits, okay, absolute value n plus 1 divided by absolute value a n. And if you do this, limits, maybe I should write it down at least. Okay, let me write it down. Okay, 2 factorial, right? Then 2 to the, okay, n plus 1 times n plus 1 factorial. So instead of n, I just write n plus 1, okay? And the times, okay, 2 to the n, okay, n factorial, n, and divided by 2 to the n, okay, factorial. Of course, there are some cancellations, right? So if you look at carefully, so these terms are cancelled out each other. We have 2, okay, these are cancelled out each other. We have n plus 1. These two cancel out each other. We have then this term left, actually one more term. Okay, fine. And if you look at carefully, and what you have here, so you have something n squared comes from here, and we have one n here, which means that we have, I mean, the degree of the numerator will be 3, if you like, and here we have only n, and when you multiply, you have terms like n squared, blah, 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 and degree is just 2, which means that if you look at the larger values for n, I mean, getting larger and larger, this approaches to infinity, okay? So fine, so what does it tell us? Since this is infinity, so it says that, so what does it tell us? Basically, this thing is divergent. So what? So we have nothing. So we cannot conclude anything. So we get no conclusion for the behavior of the original series. So no conclusion about the convergence of the original series. Okay, this one. We have no conclusion. So we cannot conclude anything if the absolute valued version of this series was convergent, then we can automatically conclude that, as we did in part B, this thing is absolutely convergent, so it is convergent. But here we end up with something divergent, so we cannot say anything about the convergence of the original series. Okay, so this is the idea. And so, therefore, we need to use something else, but still we have a problem. Actually, we cannot use alternating series. So actually, we can not use alternating series tests. Why? Right? Maybe you may ask why. The reason is actually clear, right? So because of this computation here, let me call it star. So due to star, actually you can see that an plus 1 absolute value greater than an for large n. So therefore, it's not decreasing. So it's not basically, it's not a suitable series for us to use alternating series tests. Okay, remember the hypothesis for the alternating series test. You need something, you need something decreases to 0, right? Your sequence must decreases to 0, but this is not the case. So therefore, basically we cannot use alternating series test. So alternatively, so just use the following approach. So just use something else. Need alternative approach. Need an alternative approach. So what is it? Just consider, just observe. So the following observation is enough. So you just observe that if you look at the terms which are even, even indexed terms, so n even, and let's say an, here, for instance, let's say n is 2k, okay? So with, if you like, a 2k's will be, so if you compute, so let me write it down. If you compute, you have a term like this, okay? Please check, okay? This is your even indexed terms, basically. And if you look at the corresponding part of the series, so remember, so we really understand, or maybe not observe, just look at the following, this part of the series. So just look at this part of the series, okay, when n is even. And observe that, just now observe that limit, okay, okay, fine. So maybe for the simplicity, let me denote this thing by bk, okay, and let's look at bk plus 1 divided by bk. The ratio test. We use basically ratio test for this part of the series. And then, okay, so just check. I just skip the computation, just write down, do the cancellations, and look at the limit. You will end up with infinity. So what does it tell us? By ratio test, so by ratio test, what does it tell us? This part, so an, or if you like bk, and even is divergent. Therefore, the whole part of the series cannot be convergent. And so we conclude that divergent, and so is the whole series itself, okay? Not just one part. So we just show that actually the part where your indices are even is not convergent. Actually, it is divergent. Therefore, the whole series cannot be convergent. Okay? So you have a part which is divergent, so the whole series cannot be convergent. So the original series is divergent. Okay, so this is our conclusion. You see, We have, okay, we don't have convergence behavior, neither absolutely convergence or conditionally convergence. So this series in this problem in part C is divergent. So, okay, uh, fine. And the final one, I guess part D. So what was it? Let me write it down. So part D, we have a series like this. So minus 1 to the n. So what was it? Square root, okay, n plus 1 minus square root n. Okay, so this is given. And so let's say, so for this thing, as before, we just let, okay, maybe I should write like this. So let's say this part is an. Okay, this is your an. So I guess n starts from 1 to infinity, as before. Okay, first thing, as before, you should check what about, so we just check the absolute convergence. Okay, let's check this series and just observe, okay, observe that, so what is it? N absolute value. An is just, okay, series and, okay, what is it? We just get rid of minus 1 to the n part, but we have this part. So let's try to compute this series. How can you compute this? Fine, but let's use, I don't know, you can use, for instance, the basic definition. If you remember, I mean, the previous lectures, just consider the partial sum. I mean, use definition. So by definition, by definition, remember, this thing itself can be written by using limits, right? So this is something like this. So limit n, okay, n, capital N approaches to infinity. So just consider finite sum, okay? Remember the last time. Just consider the finite sum and look at its limit. So this was the definition, right? So this was the basic definition. So let's compute. So you can easily see that. So you have limits n approaches to infinity. So let's see what we have. So this is just square root 2 minus square root 1 plus, okay, when you, okay, when n equals 2, you have square root 3 minus you have square root, okay, 2, and story goes like this. Sorry. And story goes like this. So at the end of the day, we have this minus something like this. Okay? And you see, so this term cancel out each other, this term cancel out each other. Somehow you get rid of this term at the end of the day. Fine. So what you have here, oops, I just, sorry. Oops, 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 oops. Oops. Okay, what was it? Okay, something like this, I guess, right? So we get rid of this one and the second one, blah, blah, blah. It goes like this. Therefore, at the end of the day, you have an expression like this. Okay, n plus 1 minus 1, right? Okay, anyway, so the result is infinity. So what does it tell us? Um, so it tells us as before, no information, because this thing is divergent. Therefore, the original series is not absolutely convergent. Maybe it is convergent. Okay, still it may be convergent. Okay, fine. So the second part of the analysis. So somehow we may have convergence behavior still. Just observe that. Just observe that. Okay, the first observation as before. If you look at carefully, your sequence is itself alternating. Okay, no problem. This is clear. And this is tricky. You should check. I just leave you as an okay, as a kind of exercise. So check that an is decreasing. Okay, so actually it is decreasing. So how to check? If you like, you can use the corresponding function. Just define a function f of x, which is so what was it? Okay, so, okay, of course this should something like this: x plus 1 minus square root x. Is that correct? And check that f prime x is always negative for x greater than 1. So this is your exercise. So you can check, and then we actually see that this thing is decreasing. And also, if you look at the limit of absolute value an, if you look at the limit, so what is it? So let's compute. Okay, this is n plus 1 minus square root n. Remember the trick, you just multiply everything exactly the same term but with a plus sign. Okay, something like this, right? And multiply and divide. More or less the same term but with a plus sign. Okay, n plus 1 plus square root n. Okay, if you do this, you can immediately see that this limit is, okay, what is it? So you have difference of 2 squared here. Somehow n plus 1 minus n, okay, divided by square root n plus 1 plus n. So these are cancel out each other as n getting larger and larger. This approaches the 0. So what does it tell us? A n is, okay, the given series is alternating so that absolute value n is basically decreasing and decreases to 0 actually. And so here maybe the meaning, oops, so the conclusion over here, here it says that this thing basically decreases to 0. And therefore, everything, basically your setup is ready, so you can use alternating series test. So by alternating series test, so you have alternating series satisfying the hypothesis of the theorem, therefore the series is convergent. The series, which series? This one is convergent. But remember, if you look at its absolute value, it was divergent, right? Remember our previous analysis. Therefore, therefore we say that this series an is conditionally convergent. Okay. Okay, fine. Actually, it is a good place to finish this session. And the next part, we will basically discuss approximations, okay, and using a certain error estimate theory or theorem for alternating series.